Well, I hope everybody got my email about the change to the homework assignment. Sorry for the last-minute change-up. That's one of the unpleasant surprises that sometimes arise when you're using software. Bentley in the past would give you 25 inlets on the educational version, so they really scaled that back heavy. I've sent an email asking, if there's a way for them to expand the number of inlets, and then asking also, are there similar restrictions that we need to be aware of for when I use WaterCAD in 331. A lot of you are in that class this semester, so hopefully we will have the information to avoid that in the future. I apologize. Hopefully that didn't cause too much consternation. I heard from one student this morning who was getting an error message related to not putting the inlets in a sag, but once that got sorted out, the model was converging without any trouble. By a raise of hand, did you get the models to converge okay? Yeah, nodding heads. All right. Good. Well, before we start talking about the hydrologic cycle, I want to, first of all, hand out your next homework assignment. So here's homework number 4. It's also posted electronically on Blackboard. No software other than Excel on this one. So, no HY8, no StormCAD, just Excel, I think. Yeah. Okay, so also here is a summary of the FE review sessions. Even if you are just a junior now and not yet ready to take the FE, I think it would be a good idea for you to consider these review sessions, simply because if you think about how long it'll be between when you took statics and when you do the FE, that's a lot of time to forget things. And so if you just kind of take 2 hours to refresh your memory about some of the key concepts, then that's going to really serve you well when it is time to take the exam, even if it isn't for another 6 months or even a year. So I know this class is a mix of juniors and seniors, so I'd really encourage you to consider these FE review sessions. Now, we don't have a construction engineering course, and so I guess this isn't necessarily a review, but your only chance to learn some of the material that'll be on that test. So the first session is tomorrow night, and all of them are going to be held in 1205, which is just down the hall, and they're from 4 to 6 p.m. So I'll try to remember to send out emails just to encourage people to apply, because my nightmare is that the faculty go to the trouble of preparing these review sessions and take 2 hours away from their family in the evening, and then students don't show up. That would really be a disappointment, particularly because it was the ASC student group that asked for these review sessions to be held. So I'm really hoping that they're useful, and I'm also hoping that they're well attended. The other announcement I wanted to, go ahead.
I have a question on this. So I've heard a lot of professors here have FE review like videos on YouTube also.
Yep.
So like, I know you have some, and Dr. Michelson have some. Do other professors have them as well?
There are a couple of review sessions posted on my channel that are other than like environmental and fluid mechanics. Like I think on my channel is a transportation review session. There's another one maybe that's an old statics review session. Those were recorded, I think, back in like 2013. They're pretty old, most of them. And of course, the disadvantage of a recorded session is, number one, you can't ask questions if you're confused. And then the other is it's just so easy to get distracted. If you're on YouTube, you're going to find infinitely more satisfying videos to watch than an FE review video. So I can't watch technical material. I've got to be like in a room where there's the social pressure to not get distracted and to follow along. But if you're one of the people who can do it independently, yeah. And I can send out the link to, there's a playlist of all those review sessions. I can provide you with that information. Are there any questions, other questions about the FE review sessions? Go ahead.
Will any of those be recorded?
These? Some will and some won't, but I'm not able to tell you in advance which they are, because some faculty don't mind recording their stuff and some really don't like the idea of having the recording. And so, that is something that we've discussed among ourselves, and some of them might be. And if they are, we'll let you know after the fact. But if you want the content, really the only guaranteed way to get it is to go. Any other questions? FE exam. Have any of you registered for it? Do you know how much it costs these days? 180? 120. Yeah, $120. So, I mean, that's not like the end of the world if you have to take it twice, but it would be better to just take it once. Take it once and get it over with. Be prepared. All right, the other reminder is about these co-op internships. So if you don't have another thing lined up for the summer, consider this. And then the other aspect of this announcement is if you've done one like this, or you've talked to friends and you know people who've done it, maybe share that information to some of the other students in the program. I know that the freshmen and the sophomores look up to the seniors and juniors to get information about whether it's worthwhile to do certain things. And so spread the word to any other students you know who may be in the program, because from what I've heard, of course, there's one or two students along the way who didn't have a very good experience, but for the most part, they learned some good things, earned money, and have a nice thing to add to the resume. So I think that these are a good option for summer internships. All right. So let's talk about the hydrologic cycle and precipitation. And to do that, let's first just refresh our memory about what we were doing with that pond sizing. In the homework that you just submitted, you were designing a pond to make sure that the peak flow rate gets lower for a storm. And the purpose of that pond is to make it so that a large discharge can be knocked down to a lower discharge. And it's important simply because the pipe or the creek or the river that's going to accept this stormwater could be overwhelmed by the larger peak flow. So it can be expensive, and sometimes it's impossible to accommodate a really high, quick peak flow. And if you think about before development, the natural waterways have come into equilibrium with the natural environment feeding flow. So for example, a creek that goes through your holler is sized to receive the flow from your holler when there's plants and trees and so on, leaf litter. But when people timber the trees and start putting in roofs, and if there's a commercial development with a big parking lot, suddenly there's going to be a lot more runoff coming out of that watershed than there was before. So that the creek is no longer going to be appropriately sized for the runoff coming from that watershed. So reducing the peak through a variety of methods is really important to avoid the system from being overwhelmed. And so bringing that peak down can reduce the frequency of the system failing. And this idea of there being a peak that's too high and it's going to cause problems and trying to bring the peak lower, maybe that idea and concept is familiar to you just because over the last couple of years people have been talking about flattening the curve with respect to COVID-19. The idea that we would do social distancing and wear masks and take other measures to try and reduce the number of cases that are happening at any given time. They've said now that with Omicron being so contagious that eventually everyone is going to get Omicron. And so the question is, do you want to get Omicron while you're vaccinated versus unvaccinated, and then trying to spread out the timing of that so that without any protective measures, it would all arrive so quickly that it would overwhelm the capacity of the healthcare system. And so I kind of just thought it's kind of an interesting analogy between making changes to reduce the peak and so that the system isn't overwhelmed. So you can think of the relationship there between the healthcare system and really any kind of system, whether it's roads, and there's a lot of different things that big urban areas like Los Angeles does to try and reduce the peak flow of traffic at a given time, like changing the cost of um, of toll roads, depending on if it's during the peak hours. Electricity demand, they try and flatten the curve of peak electricity demand in some places by having different prices for power during peak hours. They used to do the same thing with cell phones. Back in the days when you had to pay by the minute, there was even some plans where off-peak hours in the evening and on the weekend, it was less expensive to use your cell phone than it was during the day. And so that was just trying to manage the flow. And so that's kind of what we're trying to accomplish in stormwater management as well. So your textbook presents these different categories of stormwater storage and different ways to control the amount of water that's making it to a receiving body. And it's broadly broken up into source control methods and downstream storage methods. And so source control you can think of as prevention, and then downstream storage is reaction. And so there's examples of each of these categories, like local disposal, and we've talked about some of these already. The idea of porous pavement and trying to store water in parking area. And so let's talk about how, like, what's the method of reducing the flow rate that each of these takes. So if we can think of the rational method, Q equals CIA, Q is the peak runoff that will happen during a certain storm, then one of the ways to reduce the Q is to lower the C value of a developed area. And so anything that can enhance the flow of water into the underground rather than over the surface is going to lower the C value. And so that would be one way to reduce the runoff volume. Another is if you're detaining it at the location where the precipitation occurs, then you're having a smaller area. And so having one big area and all of the watershed flows to a big central location can be more dangerous, more expensive, and more problematic than just the local detention of flows in the location where that runoff is generated. And then trying to discharge the water to a location that's near to the source. This on-site detention is another aspect of that, where whether it's a dry pond that is usually not containing water, a wet pond that would have the water for a more extended time. These methods that are close to the source where the water is being generated usually are preventive and lower cost than allowing the water to flow to the central location where now it's going to be more of a problem. So we've already seen the video of that concrete mixer that was pouring water onto the porous pavement at the University of New Hampshire. And so whether they are these block pavers or a poured concrete that's in place that is porous, all of those work together to reduce the C value. In a lot of cities, including Huntington, there are new regulations in place that require businesses, when they're putting in pavement for the parking, that there has to be some measures to reduce the outflow of stormwater. And so there are some places in town that have porous pavement, like if you go to Cookout on 3rd Avenue, they've got some sections of their pavement is porous concrete. And I believe that they've got underground storage of stormwater at the new indoor practice facility here on Marshall's campus, where the football team practices on, I guess I said 3rd earlier. Of course, we all know Cookout's on 5th Avenue, right? 3rd Avenue is where the practice facility is. So they've got underground tanks that are perforated so that rather than flowing into the street and into the combined sewer, the water from that practice facility goes to some underground tanks, and it's just temporarily stored and then released more slowly. What can't infiltrate would overflow into the combined sewer. In some urban areas, like most notably Chicago, they have really large and elaborate vault systems that can temporarily detain storm water and You know, the land is so valuable in those urban areas that they can't afford to have surface storage of water, so they'll have underground storage, and it can get pretty enormous. The city of Tokyo is another one where, I'll try and dig up the video. There's a city, there's an underground storage tank in Tokyo where the stormwater goes down there and then they have to pump it out with a jet turbine engine because there's just so much of it and it's such a large vault. But it provides a lot of protection against the runoff. Even at wastewater treatment plants, they construct flow equalization basins to try and improve the capacity of the treatment system to avoid discharges when the big sudden surge of water comes in, and try and equilibrate and even out the flow that's going into the treatment system. Because the microorganisms that break down biological waste, they don't handle large fluctuations in flow rate very well. So you want to kind of meter over a constant flow rate into the treatment system. So flow equalization basins is just another example of trying to equilibrate and bring the peak down when it rains. Here's some pictures of flooding in West Virginia, and I think we've all become aware and appreciate the conclusion that hydrology is important in wet climates like in West Virginia, simply because there's so frequently rainfall and runoff. And of course, I've showed you before pictures of, here's Richwood. This video is kind of interesting. It shows the effects of flooding. Let's see here. I gotta pause this recording. So flooding is really important, and in arid regions, hydrology is important as well. This is a desert environment. This is a photo I think I've showed you before of in the UAE. We have a big stormwater conveyance channel that goes straight out into the ocean, and they've spent millions and millions of dollars putting in these artificial reservoirs in the mountains to try and enhance the infiltration of stormwater. If you look back in the history of Dubai, probably 30 years ago, they got the majority of their drinking water from underground aquifers. But today, less than 5% of the drinking water in Dubai comes from underground aquifers, and all the rest of it is just desalinated. And desalinated water is really expensive because you either have to boil seawater to separate the salt from the water, or use membrane filtration, and both of those are really energy intensive. And so, the cost of a cubic meter of water for us is just a few pennies, but when you're desalinating water, it can be approaching nearly $1 for a cubic meter. And so, anything they can do in arid environments to enhance the infiltration of what little rainfall they get is viewed as a good investment. So there are dams all across the mountains of the UAE where they try and retain and infiltrate stormwater down into the soil to recharge those aquifers that have been depleted over the years. Of course, there's lots of places where they don't have an adequate drainage network, just like the problem that we've got here in Huntington, where the pipes are too small or in the wrong place, or people just kick the can down the road and say, well, it doesn't flood very often, we'll just have to deal with it. And then cars get ruined. Looks like a pretty nice car. They still have the plastic on the seats even, but car won't be nice after it's been flooded like that. These are some photos that I took as I was driving around in the rain one day. One of the interesting things about certain intersections in the UAE, even like a really modern, nice city like Dubai where they spend plenty on the infrastructure, is that they just didn't plan ahead for the stormwater. And so there are certain intersections where they have to send trucks out, vacuum trucks, to suck the water out of a low-lying intersection, and then they drive the trucks into the desert and pump the water out of the truck just onto the sand. And of course, it's really dangerous to have all those trucks driving around in a heavy storm when people aren't used to driving in rain and the visibility is poor. So inevitably you'll see one of these pump trucks just wrecked by the side of the road. So I took this picture as I was driving in Dubai one day. It was an accident that happened. These trucks would sometimes be lined up 100 in a row at an intersection, just waiting for the water to go in. They pump it out, and the next truck comes, and it's really inefficient when you make a mistake with a stormwater detention facility. They went too low, and so there's just nowhere that they could take the water with a gravity-fed drainage network. Standing water obviously presents problems with safety, where if you're driving in this lane and just 2 of your 4 wheels are in the water, then that could cause an accident. And also the standing water in a warm environment is perfect for breeding mosquitoes, and so there's health hazards as well. If you've got a really nice curb and gutter, but not the drainage, then it can turn into like a little pond almost. And this is a photo that I took at the campus of the university that I was teaching at when I lived over in the UAE. And about once a year, certain parts of campus would be underwater and submerged, so you couldn't really drive around. This is completely underwater, probably 2 feet, enough that you wouldn't want to go through it. They had all this marble and granite on campus, and it was super slippery when it would rain there. Of course, it's flat, and if an impervious surface is flat, then there's not going to be a lot of water. It's not like it was inches deep, but it was a couple of millimeters deep, and it made it extremely slippery compared to if it had had a little slope, maybe a pretty typical slope for flat work like this. If you want to make sure that there's sheet flow, would be 1%. And with a 1% slope, then the water would flow towards the grass areas, and it would be less of a slipping risk for the pedestrians that are walking through the area. So just as an overview of the relationship between hydrology and hydraulic engineering, I think of hydrology as answering questions that are needed in order to perform hydraulic engineering. And so broadly, hydrology can be broken up into 2 main categories. The surface hydrology, which is the movement of water above the ground. So it would be rainfall, evaporation, and then surface flow. And then subsurface hydrology is the movement of water through the subsurface. And the subsurface can even be broken up into other categories where underground there's a certain fraction of the soil that has air in it, and that's called the vadose zone, where the pores of the soil isn't fully saturated with water. And then the saturated zone, or below the water table, is where all of the soil voids are full of moisture. So once you have performed the analysis of hydrology to try and find out what is the peak flow rate during a certain design event, then you can use that data, the flow rate that you're determining through the hydrologic analysis, to do things like open channel flow sizing, where you're trying to determine what was the required depth or the required width for a canal that would be conveying water, runoff to a lake or for irrigation purposes. In pipe flow, usually hydrology is used to determine the required drainage pipe size for a combined sewer or a storm sewer. So trying to figure out the diameter of the pipe based on the Q that is developed by hydrology. So hydrology is the first part of the design process that is done by hydraulic engineering. And hydrology is in essence, it's understanding the water cycle and trying to quantify each of the steps that begins with solar radiation evaporating water in the oceans. And it's the sun's energy that provides what's called the latent heat of vaporization, just the amount of energy required to evaporate a certain quantity of water. And so the sun shining down on the ocean causes water to evaporate. It gets into the atmosphere. And the water cycle on hydrology looks at all the different forms that moisture comes down from the atmosphere onto the surface, whether it's snowfall, rainfall, fog. All of them contribute to the precipitation that's getting back down to the surface. Now, the majority of rainfall on Earth happens back down onto the ocean, and so it doesn't have any net effect in the surface flow water cycle. But we're more interested in the fraction of the moisture that then is going to get down onto the Earth's surface. And so quantifying, and it's not just the amount so much as also the timing that we have to be able to understand when it comes to precipitation. And there's a lot of different ways for us to either measure the actual precipitation and access historical data, or to draw lessons from statistical analysis and try and extrapolate and just estimate how much rainfall would occur at a certain spot. So that's what we're going to be doing over the next couple of lectures, is focusing specifically on precipitation and what data is out there, the historical data, for example, at airports, or what statistically extrapolated data exists all over the country, not necessarily confined to airports, but what sort of data is out there that tells us how heavy the rainfall would be on a certain return period. You can see that there's a lot of other processes that also happen in the water cycle, and we'll spend some time talking about each one of these processes over the course of the semester. We'll be looking at models that describe the rate of evaporation, for example. We'll be looking at models that describe the rate of infiltration, that is, how much water can get down into the subsurface and what are the factors that influence the rate of infiltration. We'll later in the semester get into some modeling software called WMS that allows us to estimate the stream flow, the surface runoff, depending on what soil type and what land use characteristics there are. So the water cycle is a really important process. Obviously, every society depends on water, and so being able to quantify the speed of its movement through the cycle is pretty valuable when it comes to agriculture and industry and development of land for human use and protecting the environment. Just the list goes on and on. Our textbook does kind of an interesting thing and looks at the relative magnitude of the water cycle, and they normalize it to the amount of precipitation spread over the entire Earth's surface and an aerial average. If we say that there's 100 units of precipitation onto the land, then what this does is it allows us to figure out the relative magnitude of where that precipitation comes from. So for example, you can see that of the 100 units of precipitation that falls onto the land, 61% of that would come from evaporation from the land and inland waters. And so 39% of that is moisture that came from the ocean that falls onto the land. So inland evaporation is more important than ocean evaporation if we look at the entire Earth's average. Of course, each one of them plays a really important role, and there's mixture between the two, because this 100 units of precipitation, it's going to get onto the land, and some of it will go down into the subsurface, some of it is going to run off into the ocean, some of it will evaporate up into the atmosphere again. And so there's a mixture between the land-based moisture and the ocean-based moisture, but it's just kind of interesting to look in terms of the relative quantities of each from that figure in our book. Here's a similar thing that looks at all of the water on Earth and where it is. And so of all the water on Earth, most of it is in the ocean. 96.5% of that water is in the ocean, and only a very tiny fraction of it is fresh water. 2.5% of the global water is fresh water. And most of that fresh water isn't accessible to us because it's either trapped as ice caps and glaciers, or if it's not trapped, a big part of the groundwater is too deep for us to drill and get it out. So it's only a tiny fraction of a tiny fraction that we can actually access for our own uses. So it's just, I think, interesting to put things in perspective when it seems like we've got a lot of water in the Ohio River simply because, you know, we're immediately close to it, that the vast majority of Earth's water is put in places that's really difficult to use because of the salinity of the ocean, the relative isolation of the ice caps and glaciers, the great depths of groundwater that's more than a kilometer underground, and so on. There's some terminology on that handout I gave you, that list of concepts and terms, and it's important to understand what a drainage basin is, or a catchment. I just want to see if Google Earth is installed on this machine. Looks like it's not. Let me download it, and maybe when it's finished downloading.
It's like the continental divide, right?
That is, well, what a watershed is kind of depends on your area of interest. The continental divide will, let's see, where is it? I want to do the desktop. All right, we'll let this run in the background, but let's keep talking here. Okay, so if you've ever looked at a map from above that shows the creeks on it, what you've probably seen before is that a big creek is fed by smaller creeks, which is in turn fed by even smaller tributaries, and eventually you get up to streams that are only carrying water when it's raining. Those ephemeral streams that are usually dry but wet when it's raining. So when you have a high point, like a ridge line, then that's going to divide the flow of water. So yes, like the continental divide, there's a location in Colorado where any rain that falls on the east side of that continental divide will end up in the Gulf of Mexico, and anything that falls on the west side of that is going to end up in the Pacific Ocean, you know, unless it goes underground. But the continental divide is just kind of a high point which separates what direction the water is flowing. So here, this dashed line is representing the high point of a watershed, and what we would consider the watershed is basically defined by where we're interested in. So let's start Google Earth Pro, because when you turn on the three-dimensional view that includes the elevation data, you can really see pretty clearly what a watershed is. Okay, so I'm going to turn on the terrain is already turned on, and let's look at Ona, West Virginia. That's where I live, so I know it well. Okay. So what I'm going to do is, this will do as good as anything. Okay, you can, I'm sure, tell that these are where the water would flow, like these curves, and it becomes more obvious when we tilt down and look at things from an angle. Okay, so here's one. Okay, so they've built this road up on a ridge line, but as you pivot around, it's easier to tell where those high points are. So, like, I can draw it. I'll trace it first just with this cursor. So, like, when you pivot around and get a sense for the three-dimensionality of this watershed, if we wanted to know how much water is going to accumulate here, because any raindrop that falls on the surface is going to flow down, it's going to flow through the creek, and it's going to ultimately cross here. Like maybe there's a little road there. In fact, it looks like there is a road. And so if we wanted to put this road in, like upgrade it paved road here, and we wanted to have a culvert so that the water could flow under the road, we'd need to know how big should the culvert be. And so to do that, we would have to estimate the area. And so, you know, if you just want to trace the ridge line, you can do that here in Google Earth. No. This measure tool, measure a polygon. And so if we wanted the area in terms of acres, so we could start tracing, looks like maybe I need to start over here, clear. So you could trace the ridge line. I'm having a heck of a time doing this. Okay, yeah, this is working, I guess. There's an automated tool that we're going to learn when we do WMS, but what the automated tool basically does is it looks at all of the elevation data and tries to find where's the high point that defines the watershed boundaries. And so in rural hydrology, defining the watershed depends on where do you want to put the culvert, because you know the water that concentrates here, it's going to go somewhere else. You know, there's a larger watershed nested in the smaller watershed is nested in a larger one, and this nested hierarchy, which is shown here, is like if we were just interested in a relatively small sub-basin like we were just looking at, then we can trace the ridge line there. But that's going to be a part of a series of increasingly larger and larger basins that the flow rate is going to be getting bigger as the area increases. But what we would define as our watershed just depends on at what location do you want to try and quantify the flow rate. And so you find where, for example, the creek is going under the road, that's your outlet of the watershed, and then you do the calculation of estimating the area upstream from there. So how much water you're going to get out of a watershed depends on the area. It also depends on what kind of land you have. And so think about the difference between asphalt and how water falling on asphalt, there's going to be a lot more runoff and it's going to flow more quickly than if you have a natural forest litter. Another factor that determines runoff quantity is the type of soil that you have, because sandy soils are able to infiltrate a lot more runoff than soils that are clay and plastic or have a lot of salinity in them, and so that they don't allow infiltration. The terrain conditions like the slope can have a big impact on the runoff quantity, and so really steep watersheds like we have around here lend themselves to more runoff than if the watersheds were flat. And of course the rainfall characteristics also play an important role. And there are places like on the Pacific Northwest where they have fundamentally different rainfall patterns than we do, where the big thunderstorms that cause the biggest flooding risk here in the Midwest have a much higher intensity all at once compared to coastal storms where it's a more even and slow going rainfall amount. So the temporal distribution of rainfall also plays an important role in trying to determine the quantity. So each one of these factors will go into the model when we're using WMS later in the semester to try and do a really repeatable and quantitative assessment of runoff. We're going to estimate each of these factors in the models that say what is the Q that's coming out of the watershed. Each one of them will be automated so that it kind of takes the guesswork out of it. For a lot of years, hydrology was as much an art as a science, where you kind of just had to rely on your instinct and your past experience and your gut impression. But luckily, GIS and remote sensing is making it possible so that you don't have to rely on guesswork and estimation as much these days, but rather you can use satellite images to quantify how much vegetation there is in a watershed and what type of vegetation it is. And you can use actual GIS data for the soil characteristics rather than just having to estimate the soil characteristics in an area. So we have the benefit of a lot of work that's gone before us to make these estimates more accurate than they ever have been before. Okay, so just with the remaining time that we've got, let's do a review of the rational method. And this review is intended just to kind of show you the difference between, well, it's to give you confidence that you're getting the units you need in the rational method, because I've told you before that you'll get cubic feet per second for the Q by multiplying inches per hour by acres. Now that doesn't automatically follow. There's actually a units conversion there, but what this example will show you is that it's close enough that we don't have to bother with the units conversion, that we can just really put inches per hour, multiply it by acres, and get CFS from that. So this is just a review and practice problem that'll also let us look at the units. So estimate the peak runoff for this parking lot, both by method A, which is Q equals CIA with no units conversion, but then in method B, convert the given rainfall intensity from inches per hour to feet per second. So you'll have to make that units conversion and then multiply it by the parking lot area in feet. And the conversion is 1 acre is 43,560 square feet. 43,560. Okay, so by the simplified Q equals CIA method with no units conversion, if we just multiply inches per hour by acres, then you'd get 15.55 CFS. Now, let's see what the difference would be if we actually converted the intensity into feet per second. And to do that, first, we would convert 2.7 inches per hour into 0.225 feet per hour. So the length conversion has been made. And then the time conversion, we would divide by 3,600 to get it from feet per hour into feet per second. So that rainfall intensity, 2.7 inches in an hour, is the same as 6.25 times 10 to the minus fifth feet per second. Okay, and then the area, 6.4 acres, is the same as 278,000 square feet. So now we can multiply this together, also, of course, taking into account the 0.9 C value. So what we would get that way is that it's 15.68 CFS. And so the difference is pretty small. You know, the difference, if we have, let's calculate the percent difference here, 15.68 minus 15.55 divided by the one that's correct, 15.68 times 100. So the percent difference there, I think, is going to be pretty small. Less than 1%. So it's 0.8% error. So we might as well just use the easy way of multiplying the inches per hour by the acres, and we'll get CFS from that. So Now we've proved to ourselves that it's not too much of a correction factor issue. Any questions? Go ahead.
If you do like the other units.
Metric, yeah.
Metric, sorry, yeah. If you use metric units, would that work if you like would use like what?
So for metric, we have to do it this second way. We have to have the rainfall intensity in units of meters per second,
Mhm.
and the area of the watershed in terms of square meters.
Gotcha.
Yeah. It's just an odd coincidence that inches per hour in acres gives you the CFS. So there's no equivalent for that in traditional in SI units.
Gotcha.
Okay, that's it for today. Remember, I've just given you the next homework assignment. I don't think there's really anything you can do quite yet to get started on that, other than there is one thing. There's a website where I suggest that you download some precipitation data. I tried it out this morning. It's working, and it only took, I think, 20 minutes for me to get my data. But in the past, some people have taken like a couple of hours to get the data off of that government website. So if you want to get your order in early, then you can download the data now. Otherwise, I'll show you more about that website, and we can do that later.
Would there ever be a scenario where you want